Hi everyone, we are looking at some more volumes. So we're going to revisit a couple of old functions. We have y equals x to the 2/3 and y equals tangent x. And we're going to let R be the region bounded by those graphs. Region R, that region here, is the base of a solid whose cross sections perpendicular to the x-axis is a right triangle. One leg is the length of its base and the other leg, the triangle's height, is 3 times that length. Find the volume of this solid. And you might be just like going, what? Okay, so let's break this down really carefully. So this region is my region R. Cross sections perpendicular to the x-axis. So here's my sample rectangle. Like that. And what I have is a right triangle that's sticking up out of the page. And here is the trick to trying to draw this, because I obviously can't draw something that's coming straight out of the page. But if I kind of tip my x and y axis over, so I can have my function like that for my tangent x, and by the way, let's do some defining here. That was my y2 is tangent x in red, and in blue I have my x to the 2/3, so that's something like that. So if I draw it like this at this kind of wonky angle, and I'm going to define my x1, y1 because it matches what I have in my calculator. And so it's going to help me write things soon. But also when I'm writing, all I have to do is write y1 and y2. So I have this x to the 2/3 in blue. So now to try to draw this, my sample rectangle, notice how this sample rectangle, it's running parallel to the y-axis. So I'm going to draw myself a triangle a rectangle of sorts that is parallel to the y-axis-ish. So here's one leg of my right triangle. The other leg, the triangle's height, is 3 times that length. So I'm going to go straight up. It's not going to be 3 times because of space, but pretend it is. So it's going like that. So my right angle is at the top right there, and it comes down. So here's my right triangle. There's my right angle. And so rather than trying to even consider drawing this whole entire shape, I'm just drawing one slice, because remember, we don't care about the whole thing, we just care about one slice. Okay, now that I'm here, so if I look at my original guy, because that's sometimes helpful, this is dx on the thickness. And then the vertical dimension on this is the blue minus the red, or y1 minus y2. Which means coming over to this kind of slanty drawing, I have my dx still. Across the bottom, or the length of the shorter leg of the triangle, is y1 minus y2. And then here, if it's 3 times that length, it's 3 times y1 minus y2. So now I've set things up with some things labeled. Now remember, every time we're doing this, we have one technique, and that is this. Area of the slice times the thickness. So when we look at this, we're like, oh, it's a right triangle, 1/2 base times height. And then our thickness is going to be a dx. So I have my 1/2. My base is my y1 minus y2. I could even make myself a note that this is the base, and that this guy right here is my height. So I have y1 minus y2, and I have 3 times y1 minus y2, and then dx. Okay, so this is my general setup. I can obviously tidy it a lot, so I can do that. So I have my 1/2 times 3, so 3/2 y1 minus y2 squared dx. And then the other thing I need are some bounds. So if we look at our graph, I've already made this graph. We have 0, 0 is one intersection point. Remember, we can do that intersection, so second trace, intersect. First curve, we're on y1, so we hit enter. Second curve, y2, enter again. And I'm pretty close to that spot, so I can hit enter again. And I get this 0.6375 ... and I'm going to define that on my paper too. A, and I'm going to call it A because I'll store this in a moment. So here's all my defined stuff that I can use it, and now that I've written it one time, I can just refer to it. So it's really convenient that way. Okay, so back to my calculator, I have that 0.637. Right now it's currently stored as X. I want to keep it for later, so I'll hit store and A, and it's ready to go. So now on my paper, I have my 0 and my A for my bounds. This is telling me exactly what I need to type on my calculator. So the only thing I need left is a number because this is a calculator question. So I have my math 9, 0, and A. And then watch the parentheses on this. I'm going to just type 1.5 because it's easier. And then parenthesis y1, so alpha trace y1 minus alpha trace y2. Parentheses squared, and then dx. And before I hit enter, I'm just going to take a quick look at this, make sure these two look the same, and they do. And I get 0.011. So one thing to note, because you did this problem, you found this area on our area assignment, and the area between these two curves is 0.064. And this will throw students off a lot because there are times you'll see the same situation with multiple applications, like part A, find the area, part B, find the volume for like this, and so on. And then students get really freaked out because they're like, wait a minute, my area is 0.064, my volume is 0.011. How can my volume be bigger than my area? Well, it's not. It's a different thing to compare, because remember, this is a cubic unit versus square units for area. For example, if you have a square that's 0.2 by 0.2, your area is 0.04, and if that was a cube, it would be 0.008. So numerically your area is bigger. But if I compare a 2 by 2 square versus a 2 by 2 by 2 cube, the volume is numerically bigger here. So the whole point of this is areas and volumes don't compare, because you can't really compare square units and cubic units because they're entirely different things. So it's just something to note, because I've had students get really confused on that. Okay, but once again, as we do these problems, the thing to keep in mind is right here that no matter what it is, you don't care about what the whole thing looks like. I have no idea what this whole thing looks like. I don't care what this whole thing looks like. I care about one slice, and I say, what's the area for my peanut butter, if it were a piece of bread, times my thickness dx or dy, and then integrate it to get the whole thing.